Alright, geometry, I'm back. I had a busy couple of days, but now it's Sunday morning. I'm ready to get back on it. Okay, page 511, number 3 here is we got two similar cylinders, which means they're the same shape, just different sizes. So since this one has a radius 3 and this one has a radius 4, this one's going to be a little bit taller. To sort of match the ratio of that on this one. A is about, what's the ratio of their heights? Well, you could do this as 3 over 4. You could do it as 4 over 3. I always like to go big over little. So I'm going to say here a ratio of length here is 4 over 3. And the first question about height is a one-dimensional measurement. So that's also 4 over 3. Question B is, what about base circumference? And circumference, if you think about it, is just a curvy line. It doesn't have any two-dimensional area. It's just really a length. So it's also just regular old K. Part C says lateral areas. Lateral areas, well, of course, that's an area. So that's a two-dimensional version of the similarity. So that's a squared K. And D is about volume. Well, same sort of story. The ratio of lengths is 4/3. The ratio of volumes is 4/3 cubed. That would be 64 over 27. 64 over 27 is a very popular answer, you notice, because this book likes whole number answers. Same sort of question here in 4. We've got two similar pyramids. They give you two linear measurements on there. So I would say that here my K equals big over small, which is 18/12, which I can't help but reduce. That would be 3/2. 3/2 is going to be the ratio of anything linear, and then anything area-wise would be 3/2 squared, and anything volume or weight-wise would be K cubed, or 3/2 cubed. A is base area. Base area then will be a K squared situation because it's area, two-dimensional. There you go, 9/4. Part B says lateral areas, same thing. Part C, total area, same thing. Wow, this is a really interesting question. And number 5 is volume. Volume, we finally get a little something different. Volume is a three-dimensional measurement of the shape. So you have to cube that. 3 cubed is 27, 2 cubed is 8. Again, whole numbers. What I mean by that is they take whole numbers and cube them. So when you see a ratio like this, and you know it's K cubed, and you got to find, like this one, and you got to find the cube root of it, it's always going to be whole numbers in this book. Now, I can't promise that on the test. In class, we worked a lot on, if you knew this and had to find this, you could use the cube root button on the calculator. So be careful of that also. Okay, 10 is about a model train, and the ratio is that it's a 1/48 scale. You could write that this way too. And when they give you that scale in models, we did this on the old, I don't think it was first semester, test about how to scale down models and stuff. When they give you this as the ratio of the scale factor for the model, they're saying any length on the real train sort of gets divided by 48 to become the length on the model. The model is 1/48 the size in terms of length. That's just a regular old K model, or K ratio. That's every length on the model can be explained as 1/48 of the real life length. Okay, so the scale for the model is 1/48. If the model hopper car will hold a volume of 90 cubic inches, so this is the model volume. Sorry, is it the real one or the model one? The model. 90 cubic inches, and this is the small one. This is the. Gosh, that's huge for a model. Wow. Okay. What is the capacity in cubic feet of the actual hopper car? Okay, so we need to take 90 times that ratio cubed. Oh, you know what? This is small or big. I need to divide it then, don't I? If I divided 90 by 1/48 cubed, it would be really super tiny. So I need to. Sorry, if I multiplied by 1/48 cubed, it would get really super tiny, so I have to do this. Or I could rewrite this as 48 over 1 and multiply by 48 cubed, which is what I'm going to have to do anyway to figure this out, and I get the volume of the big one. Alright, let's get the calculator out. I'm taking 90 divided by 1/48, which is the same as this, and I get a huge number. I'm supposed to change that to cubic feet. Alright, so this is cubic inches. How many cubic inches are in a cubic foot, you ask? We've talked about this in class. There's 12 cubed cubic inches in a cubic foot. And so when I divide that out, this is now cubic feet. You know, I could have changed the 90 to cubic feet in the first place. That would have worked too. 5,760. Exactly. That's huge. Wow, I didn't realize change was that big. Okay. All right, in the name of jumping around. Oh, you know what? Before I do this, I was going to show you. The last problem, I changed this to, I mean, that's the answer, 5,760 cubic feet. But I also wrote this number down here for cubic inches, because if you do this calculation, you get that, and people are going to go, where'd that come from? So I can also say this. 1 cubic foot equals that many, because it's k cubed, cubic inches. And that's how we did that conversion. Okay. So yeah, in the name of bouncing around, here's page 501, number 24. The question is about, okay, there's 4 balls in this can. The question is, if you melted all this down, could you fit 2 more spheres worth of material inside that can also? So you need to figure out how much of the volume sort of is taken up by these things. One way to do this is to make up an actual number for R and try to figure out what volume is left over, but be careful when you do that, because I mean, it would actually work here, but sometimes that doesn't work. So in the name of algebra, let's just try to do this in general. All right. So the volume of one sphere, we're going to find the volume of each sphere. We're going to find the volume of the can, and we're going to see sort of like how much is left over in terms of numbers of spheres that are sort of stuck out here in empty space, not filled up by the balls in that can. Volume of each sphere, of course, is 4/3 pi r cubed. The volume of the can is the area of the base times the height. Well, the area of the base is no problem. It's pi r squared. But what's the height of that can? And this is really the whole reason why this is a hard, why this question is so far down the list and why it got asked. Well, the height of the can is 4 spheres. The height of each sphere, well, that's just the diameter of the sphere, and that's 2 times the radius. That's radius and radius. So altogether here, I'm going to have 8 radii of height, if you think about that. So base times height is that, which is 8 pi r cubed. Well, I just need to compare 8 pi r cubed to 4 of these. So 4 sphere would take up 4 times that, which is 16/3 pi r cubed. If I subtract those, what's the space? Well, what's nice is I have like terms in pi r cubes. So I just need to take the 18 minus the 16/3. If you remember your fraction stuff very well, that's like taking 24/3 minus 16/3. What I have left is then 8/3, and guess what? So I'm talking about 8/3 pi r cubed of space, and wouldn't that equal 2 of these? Equals 2 sphere. Of course, because the sphere is 4/3 pi r cubed, 2 of them would be 8/3 pi r cubed, and that's exactly how much space you have left in the can. Cool. Well, 25, first of all, this is a problem I remember doing a lot with people in class, and the intention is, you have this time in class to ask me questions. I'm kind of annoyed that I have to do this again here, but I'll do it. Volume of the cylinder in terms of R, well, we just did that over here. I'm surprised they're asking that number 25. Volume of a cylinder is area of the base times the height. Area of the base is no problem. It's pi r squared. Height, just like we had on the last problem, the height of this little can is 2r. So this turns out to be 2 pi r cubed. Uh, 26, same picture. We're talking about you're supposed to examine the surface area of the sphere and the lateral area of the cylinder and see how they compare. The surface area of the sphere, of course, is just 4 pi r squared. Whoa, 4 pi. I started making it 4/3. Don't do that. 4 pi r squared. Lateral area of the cylinder is perimeter times the height. Well, the perimeter is 2 pi r, and the height we just worried about was 2r. Write that here because I'll need it to look, actually, when you look back at 25, times the height. Well, if you take 2 pi r times 2 times r, I have 2 times 2 is 4, r times r is r squared. I have this, and guess what? They are the same. So, yes, that's true. 27, you're probably looking at going, what in the world is someone thinking with this double cone thing? You'd be amazed how much the double cone is going to come up in further math courses. Anyway, you're supposed to find the volume of this shape that's left here. Sort of, if I take the cylinder and subtract out this cone. Now they also tell you that the height of, okay, this is r, this is 2r. So we're really talking about the same kind of looking cylinder as this one. So, and that comes back later, just keep that in mind. So the volume of the cylinder, we're just going to do volume of the cylinder, the plan here, minus the volume of 2 pyramids. Sorry, those aren't pyramids. Those are cones. Okay. Yeah, remember this. The volume plan is always pretty intuitive in terms of what you can add and subtract when you have a crazy combined shape like this. This really was, there was a cylinder and you took out 2 cones. Now, if you had to find the surface area of this, much harder. I won't even explain that now because it's not this problem. It will certainly come up in another one. Okay, volume of the cylinder is, well, we just did that. It's right here. It's 2 pi r cubed. I don't even want to figure that out again. It's the same thing as what I just did. Why do it again? 2 times the volume of a cone. Now, the volume of a cone is 1/3 area of the base times the height. Now, what's the height of that cone? Well, if it's 2r from here all the way to the bottom, this would be 1r. So that's times r. Let's simplify this a little bit. 2 pi r cubed minus, now I have a pi r cubed here, which is kind of nice. That's sort of thinking that maybe I can, what? I wrote squared. It was cubed. I have like terms here, and then I just have 2 times a third of them. I have 2/3 of them. So I have 2 pi r cubed minus 2/3 pi r cubed is, well, that would be 6/3 minus 2/3 is 4/3 pi r cubed. Have you ever heard that number before? Interesting. Okay, we have a snowman here on page 511, where the diameters of the 3 snowballs are 30, 40, and 50, and they tell you how much the head weighs. The head weighs 6 kilos. How much should everything weigh? First of all, we have to find the total volume of snow, and then I'll translate this volume thing using this, what I know about this snowball and how much snow's sort of density is. The volume of the head, I'll say top. The volume of the top one is 4/3. This is a long problem. 4/3 pi r, remember radius to be 15 here, cubed. Volume of the middle would be 4/3 pi. I think there might be an easy way to do this all in one step. Radius is 20, and bottom looks like this. 25. You know what? These are all like terms in 4/3 pi. I might just want to go 15 cubed plus 20 cubed plus 25 cubed. Let's just do that. 15 cubed. Wow, this is a lot. Plus, it'd be huge numbers. 20 cubed plus 25 cubed. Oh my gosh. 27,000. That's nice. Total is 4/3 pi times 27,000. Adding those all up, and 4/3 of 27,000 I can do times 4 divided by 3. I get 36,000 pi. What a nice number. Okay, well, I'm told then I have to figure out the weight of 36,000 pi cubic, whatever these are, inches of snow. That's probably centimeters anyway, because we're talking about kilos. So I know that this much also equals 6 kilograms. And how much was that in snow? In just raw pies of snow. That was 15 cubed times 4/3 was something like 4,500. If 4,500 pi weighs 6 kilos, now this is a volume measure and this is a volume measure, and I want to figure out from this volume measure how much, volume measure and weight I have. So it's just a straight proportion at this point. If 6 kilos weighs 4,500, I can just say 4,500 pi over 6, 4,500 pi actually. 4,500 pi weighs 6. So how much should 36,000 weigh? I just take 36,000 divided by 4,500 to figure out how many head sizes we actually have worth of snow, really. Divided by 4,500. And then I'll take that times 6. That's how many heads of snow really we have. So we have a total of 64 kilograms total. Okay. I'm not going to have enough time to do number 15 on this video. I will next do another test review one, and I'll get back to this one after that. Enjoy.